Okay. Fantastic. So let's just keep going. Just hop into this, right? So this section's shorter. You know, like a couple things really to do. I'll give a couple examples. Of each thing that we're gonna up to date, but we need to cover area and links and polar coordinates. Okay, so we're going to be finding, right, doing integrals essentially of polar coordinate stuff. So yeah, we'll take it. We'll take a moment here and just let's assume that I have a polar curve. Okay, and we'll just draw like something that's a bit simpler. I mean, not just doesn't have to go through something lines. We'll draw something that's like this, right? And let's say that I want to find the area underneath this polar curve. Okay, up until between this angle and this angle, or maybe over here. Let's say that it goes a bit farther here. Okay, let's say that I want to find the area between these two angles that goes from my curve down to the origin. Okay. So normally when we're doing integrals, right, we want to set up things in terms of rectangles, right, to approximate, but that's going to be a little wonky here, of course, you might imagine, just because how it circles around, right? I can't just stack them. I can't stack in rectangles the same way I normally would. So when we're finding the area of this, what we're going to use instead is we're going to use like just take a tiny sector, like sectors of this, and add up the areas of those, right? Because remember, if I'm finding that, if I have a circle, right? Right, just a neat circle, right? Very neat. And then I want to find the area of just a piece of the circle, right? So let's say, so here's kind of the center of the circle. Okay. If I want to find the area of this piece, right, that has angle theta, and then the circle has a radius of r, right? How do I find the area of this piece? Right? Who remembers the equation for this? I actually mentioned this. Yes, yeah, you would actually just integrate kind of the arc length, which you don't really talk about when you do it. The arc length, is r times theta. So if we just kind of in a way took and integrated the equation with respect to r, right, and left the theta by itself, then we get the formula. Now I don't want to show it that way, just because I'm not 100% sure if that's how they, because there's other ways we could get the same result. But the area of this sector is equal to 1/2 r squared theta. Okay, so that's just the general formula you should remember, right? So the area of the sector of this circle is 1/2 r squared theta. So what I'm going to do is I want to take little pieces of this curve and I'm going to break it up into sectors, right? Now for each of those sectors, I'm going to work on those sections as if it was a circle, right? So I would just take the radius of that section and I would add up all those pieces together, right? And that would be at least an approximate version of my area, right? So to break it down a little bit, right? The area of each of these sectors, I'll call AI, or maybe we call it delta AI. I'll just call it AI for now. Is going to be 1/2 times Ri squared times theta. Oh, they use delta theta. Okay, because I want to have, just like when I have delta x, that's consistent. I'm going to use a delta theta, right? Kind of a general change to my angle, right? So this is the area of each of my individual sectors, right? So if but this radius, right, should be an equation something like this, like r equals negative sine of 5 theta, right? So our I itself is some f at some theta I, right? It's my function, whatever the radius is, evaluated at some theta, right, in between there, okay? So I'm going to rewrite this as 1/2 times f of theta I squared times delta theta. Okay, now, whenever I find the area of the whole thing, I just want to take all the pieces and add them up, right? And we're going to take the limit as n approaches infinity. So we're going to go from I equals 1 to n of 1/2 times f of delta theta I squared times delta theta. Okay, but we have theta instead of x here, but this is still precisely like this is in the form that we like when it comes to Riemann sums, right? So I can take this, as I take it towards infinity, it's going to become an integral. So this limit is going to be equal to the integral from, and I'll use alpha to beta here again, just like kind of like a parametric one, but this time they're using the angles of 1/2 times f of theta squared d theta. Or I might write this as integral from alpha to beta of 1/2 r squared d theta, right? Because that would just be r is just whatever the formula is that I'm given, okay? And this formula, so maybe again, let me write it big for us so we can see it. Area is going to be the integral from alpha to beta of 1/2 r squared d theta. Okay, so if I to find the area underneath this polar curve, I use this formula to do it. Okay, and that'll give me what I want. Okay, so to start us off, we are going to find the area underneath one stem of this guy right here. Okay, so the area underneath one stem of that curve. Okay, so one stem, right? All it is just one little piece of it, right? So we don't need to go all the way over here to get that, right? Let's just go to where our first stem was, right? Our first stem was the one that went from 0 to pi over 5, right? Because when I went from 0 to pi over 5, I would get, that gave me this guy. Okay? Hit and right, 0 to 0, and then it goes in between, so that's the piece, that's my stem. So to find the area of this guy, I'm going to take, or one stem, which we're finding this one in specific, but it's the same area for all 5 of them, is going to be the integral from 0 to pi over 5 of 1/2 times sine of 5 theta squared d theta. Right? That's the formula we use. Okay, now we know how to calculate this. Might take a bit, so we'll again, every time I'll bring it up over here so we can work on it and leave the picture up in the meantime. But yes,
Will be given the upper bound. We don't have to do all of this.
no, not always. Sometimes you will have to sketch though, but it may not be that complicated. It may be something simple. Okay, but sometimes you might. You still need to know how to sketch. Okay. So we're gonna get 1/2 in this case. So again, I'm gonna kind of cut this off where we do it this way. I'm gonna bring out the 1/2, and we're gonna do integral from 0 to pi over 5 of sine, and I'll bring that square inside, kind of where it normally would be on here. To that point. Okay. Now, if I want to find the integral of this, what do I do with that sine squared? How do I rewrite that? There's a way I can rewrite it. What is it? One minus cosine. Yeah, so you're thinking of the Pythagorean identity. We want to use the kind of our double, like the identity we have to transform the square into just like a 1 degree thing, where we take 1 minus cosine of 10 theta over 2. Again, because we take 2 times whatever the angle is, so it's 2 times 5 theta, which would be 10 theta. Okay, so let me write this again. So 10 theta. So from 0 to pi over 5. Okay. Now, we can bring that 1/2 out, so I'm gonna get 1/4 integral from 0 to pi over 5 of 1 minus cosine 10 theta d theta. Okay. What's the integral of 1? Theta. And then what's the integral of cosine 10 theta going to be? Right, what's the integral of cosine theta? Sine theta. So I'm going to have sine theta, but then I just multiplied by 1 over 10. Right? Or you can do u sub, that's fine, but shortcut is just to divide by whatever the constant is on the inside. And then 1/10 times 1/4 is 1/40. And then we're going to evaluate this from 0 to pi over 5. Okay, luckily, 0 makes both of those terms 0, so we don't have to worry about that. So we're, and this is not just sine theta, this is sine 10 theta. Okay, so we're going to get 1/4 times pi over 5 minus 1/40 sine of, what's 10 times pi over 5? 10 times pi over 5. 2 pi. Good. What is the sine of 2 pi? 0. Okay. So that whole part just goes away. Luckily, that's nice. So then we just have 1/4 times pi over 5, which is what? 1/4 times pi over 5. Pi over 20, right? It's 4 times 5, right? Pi over 20. Okay, good. So I was going to leave part of this off, so I'm sorry if that was got squeezed in a little bit. Maybe let me erase some of this over here and I'll write it out for those who might not be able to see it too well. But essentially what happened, right, is we said, okay, I want one stem of this, which I just need to go from 0 to pi over 5 for 1. That's all I need. So we said the integral from 0 to pi over 5 of 1/2 times sine of 5 theta, which would be negative sine 5 theta in that case, but it doesn't matter much with squared, right? Squared d theta. Okay. And then I pulled out the 1/2. And then the negative goes away, so we just have sine squared 5 theta. But then we write sine squared is 5 theta. We can use our identity we had learned from 7.2 and use a little bit after that, where we have 1/2 integral from 0 to pi over 5 of 1 minus cosine of 2 times theta, which is 5 theta. So we get cosine 10 theta over 2 d theta. I can take out the 1/2, so I get 1/4 integral from 0 to pi over 5 of 1 minus cosine 10 theta d theta. And then from here, we can integrate this directly. So I get, so that's going to give me 1/4 times theta minus, and then the integral of cosine 10 theta would be 1/10 sine 10 theta. And we're going to evaluate this. We'd evaluate it from 0 to pi over 5. 0 is going to make both terms 0 because we get 0 minus 1/10 sine of 0. Or, 0 minus 1/10 sine of 0. And then we get 1/4 times theta, we put in pi over 5, minus 1/10 times the sine of 10 times pi over 5. 10 times pi over 5 is going to be 2 pi. So we get sine of 2 pi. Okay, but the sine of 2 pi is 0. So that part just goes away. So we just have 1/4 times pi over 5, which is pi over 20. Okay, does that make sense? So the hard part, probably the whole problem would just be graphing the thing, right, in the first place, right? But once you have that, right, you can just see, oh, well, one stem would just be 0 to pi over 5. And so that would be my answer, right? So that's my area. Does that make sense? right? Again, you just find how long it takes for you to do one stem, which are just 0 to 5 or 5 in this case, might be different in other cases, and then you plug into the formula and find the area. Okay, good. Now I can erase this. And we're going to do another one. Actually, a couple more. So next, we're going to do problem number 26. Let's see. 36, 26. Oh, that's right. So that was an example of one where you just have to just find one stem of it, or you're going to encounter some problems that just say find the area of the region bounded by the one curve, right? So you just have one polar curve. So you might sketch it real fast, do your process. Hopefully it'll be fairly easier to sketch. And then you're just going to find, if it gives you bounds, you'll use that. If it gives you, certain point, you just plug in certain points and you're going to find the integral from that. Okay. So let's go ahead and move on to the second example, where instead of just doing one, right, we're going to be doing two curves where you're bounded in between two curves. Okay. So we want to, in problem number 26, find the area enclosed in inside first curve and outside second curve. Okay, so the two curves that we're given are r equals 1 plus cosine theta. So this is my first, and then my second one that I'm given is r equals 2 minus cosine theta. Okay, so again, it lies inside the first curve and outside the second curve. Okay, so that's the first, this is the second. Okay, what I'm going to strongly encourage you to do here, even if you don't like it, is to try to sketch it. Okay, these ones are a lot easier to sketch. It won't take you as long. Okay, because it's just plus, minus, and it's just one theta, right? So I'm going to take some time on that. So I'm going to sketch these out. Okay, so we can do the plots, right? To get each one, right? So in this case, for the first curve, we're going to have, let's see, 1 plus cosine theta. So I just take the cosine curve and I move it up one spot, right? So I'm going to have, so it normally would be at 1, but now it starts at 2. And then we're going to have something that looks like this. And then we're going to have a second curve. Second curve is going to do, let's see. So now our cosine curve is going to be flipped. And then we're going to move it up 2 spots. So it would be flipped. So it should start down, but should start down here and then work its way up kind of like this. But we need to move it up to 1, 2. So something like that. So this is my curve. Okay. Again, this is 1. This is 1. This is 2. So the highest of this one goes is 3. Highest this one goes is 2, and then it goes down to 0. Right, but that's going to be what the curves look like. So these ones are going to be easy because they don't pass underneath the x, right? So it's just positive all the way. So whenever I'm at 0 for theta, I'm going to start at 2 in the r, right? So theta equals 0. I start at 2. So maybe again I'll indicate this one by blue. This one by orange. Okay, we're going to start out at 2. And then whenever we're at pi over 2, I should be at 1. And then when I hit pi, I should be back at 0. Whenever I get to 3 pi over 2, I should be back at 1 again. So that's my blue curve. Okay, and then my second curve, the one I kind of labeled orange here, real fast, is I'm going to start at, when I'm at 0, my radius should be 1. Okay, whenever I'm at pi over 2, my radius should be 2. So it should be here. Whenever I'm at pi, I should be at 3. So 1, 3 about. Okay, and then we go back down to 2, down here, and then we're going to end up back at. So maybe something like this. Okay, so what it asked for is that it wanted the area enclosed inside the first curve, right, which is the blue one, and it wanted outside of the second curve, which is the orange one, right? So we want outside of the orange one and inside the blue one. So is it going to be in here? Right, it's not here, it's got to be here. Inside the blue and outside the orange. That's only here. Okay, outside the orange it tells everything out here, inside the blue it tells everything here. So the only spot that we can work with is going to be, which I'll call color white. Okay, good. Now, just like when we did area between curves, right? I'm going to need to know when these two hit each other, right? Because that's going to tell me when to stop, right? I don't want to integrate too far to the left or to the right. So if I want to find where these two curves intersect with each other, what should I do? Set them equal to each other. So I'm going to take 1 plus cosine theta equal to 2 minus cosine theta. Okay. So I'll add cosine to both sides. Subtract 1 from both sides. We're going to get 2 cosine theta equals 1. So we're going to get cosine theta equals 1/2. So what is theta? What angle, what small angle makes cosine equal to 1/2? Not pi over 4, not pi over 6, pi over 3. Now, I could either do, well, actually, no, you can't. You don't want to do that. Okay. If you were thinking, okay, well, the other angle I'm going to get, right? That has to be, you know, I'm going to get the angle that's in this quadrant, and so you might say, oh, well, it's 5 pi over 3, right? If you were to find that, right? But the issue is you don't want to use that because if you say pi over 3 to 5 pi over 3, you're going to go all the way around. But we don't want to go that way. We want to go in here. So if I don't want to use 5 pi over 3, I want to use whatever the angle is that's in the same spot that's going to come before this positive pi over 3. Negative pi over 3. This cosine is still positive in the fourth quadrant. Okay, so negative, so that quadrant is going to work. And 5 pi over 3 is the same thing as negative pi over 3. So we need to use negative pi over 3 instead. Okay, which shouldn't be too hard to see from the picture if you sketch it out. Just be careful with that, make sure your integral makes sense. So we're going to go from pi over 3 to negative pi over 3. Good. Okay. Now, working kind of backwards here, but that's okay. We're going to take the integral. Okay. Now, what's going to happen, right, is I want to have this mentality where I'm saying, okay, I have the area of the outside curve and I have the area of the inside curve, right? and we're gonna subtract those two, right? So finding them both separately, right? So let's say I have, you know, r equals f of theta and r equals g theta, and I want to find the area between these, right? And this one's on the outside, this one's on the inside, right? If I were to do them separately, right, I would find the area of this one, right, which would be the integral of 1/2 r squared, which, sorry, I'll do f of theta, d theta from alpha to beta minus the integral from alpha to beta of 1/2 g of theta squared d theta, right? I just subtract the two areas and that gives me the area I want. But I can just simplify the process, right? And instead of doing two separate integrals, I'll just bring them into the same one because it's the same bounds. So I'm just going to do the integral from alpha to beta of, and I'll break the 1/2 out, and we're just going to find f of theta squared minus g of theta squared d theta. Okay, this is the area between two curves. If I just want one curve, right, I don't have to worry about this part, but if I want two, I need to be subtracting both of them squared, not just subtract the two. Okay, so we're going to have 1/2 integral from, now we're gonna use this for my actual problem, right? So my bounds are what? What are my bounds gonna be? -π/3 to π/3. Good. And then we're gonna have f of theta, which in this case is it's inside, so we want 1 plus cosine theta squared minus 2 minus cosine theta squared d theta. Okay, so then we have to take these things and we're at the square root. So I'm going to get 1/2 integral from -π/3 to π/3. So we're going to get, so what am I going to get when I square 1 plus cosine theta? Anybody? What if I have two terms and I square it, what do I get? Oh, wait.
Plus 2 cosine theta plus cosine squared theta.
Good, thank you. Yep, so we square the two terms and then we take the two terms multiplied together and multiply by 2. So we get this. Okay, and then we're gonna have minus, we're gonna have 2 squared or 2, yeah, minus 4 cosine. Good. Okay. And then theta. Okay, so it looks big, right? But something really nice is going to happen, right? Because the hardest part of the integral is going to go away. Cosine squared theta minus cosine squared theta cancels out. So I'll go ahead and bring it back over here now. Probably good with our picture. Probably figured out everything we need to. So we're going to get 1/2 times the integral from -π/3 to π/3 of, so we're going to have 1 minus 4. What's 1 minus 4? -3. And we have 2 cosine theta plus 4 cosine theta. And then cosine squared minus cosine squared is 0. So we don't have to worry about that. So we just get d theta. Can I integrate this? Pretty easily, actually. Yes. So I'm going to get 1/2. What's the integral of -3d theta? What's the integral of 6 cosine theta? Not 3 cosine squared theta. I don't integrate. I can't just do the power rule. Plus 6 sine theta, and we're going to evaluate this from -π/3. Okay, so let's do that real fast. So I'm going to plug in. I'm going to get 1/2 -3 times π/3, just -π. And then we have plus 6. What's sine of π/3? Sine of π/3. Anybody? √3/2, right? √2. Okay. And then minus, now I'm just going to do 1/2 again here. -3 theta times -pi/3, which is going to give you a positive pi in that case. And we're going to have +6 times, what happens when I put -pi/3 in for sign? Yeah, nope, that's good. -3/2. Yeah. Okay, awesome. So in the end, what's going to happen is I'm going to have, so I have negative, so there's a 1/2 on the outside, so that'll just come at the end. But I have negative pi minus pi, so I have 1/2, and I get -2 pi, and then we're going to have 6. So what's 6 divided by 2? 3. Okay, so we have 3√3 minus -3√3. So what's 3√3 plus 3√3? Plus 6. Okay, well, taking the 1/2, we're going to get, and I might flip the order, I'm going to get 3√3 3√3 minus. Okay. Understand? Sometimes when I do this, well, I'll try to give easy ones that are straightforward. But I think book examples are good ones. Sometimes they take a while, so that's okay. Okay, let's wrap this up real fast. We're gonna do number 38 real fast because we just want to get more practice of this again, right? 38 says find points of intersection. Because when I'm finding these areas between curves, I want to know where they intersect each other. So it's going to be good for us to practice this a little bit. So the example I picked for us here is going to be, we're going to do R equals 1 plus cosine theta, and R equals 1 minus sine theta. So we want to find where these two graphs intersect each other. Okay, and if you want to find, we want to find all of them in general. Okay, so you can kind of express it as a general sort of statement, but we need to find all of the intersection points here. Okay, so how do I find the intersection points? Well, how should I start this? Good. So we're going to get 1 plus cosine theta equals 1 minus sine theta. Okay. What's next? Yeah. Put it on there. So we'll get cosine theta equals negative sine theta. Okay. Now we can make this more complicated than it needs to be, or we can just, make this pretty straightforward. Because there's we could make it so we could solve this. Like you might be able to square them and get a relationship between it. But let's just think about it, right? We want places, if I ignore the negative sign for now, I just want places where cosine equals sine. What angle is cosine equals sine? It's pi/4, right? But, so the reference angle we want to think of, right, is pi/4, right? But I don't want to just use pi/4, right? Because that's not actually correct here. I'm going to get √2/2 is negative √2/2. I need the quadrants where they're going to have different signs because they need to be the opposite of each other. So what quadrants are they going to have different signs? 2 and 4. Good. So if I use this reference angle, what is going to be the equivalent angle in this quadrant? Good. It's going to be 3pi/4 because I can just take pi and subtract pi/4 from it. So and then what's the angle going to be in this quadrant? 7pi/4. Again, you subtract pi, you can take pi/4 from pi. Okay. And finally, we want to do all the points of intersection, all the possible points. So remember that in trig, we always, when we were solving equations like this, we always want to do a plus 2 pi n on each of those. Okay. Now, this is completely fine. If you did this, it's okay. There's actually, it is a little simpler to like write this actually, because notice both of these angles are just a pi away from each other. So I could also write this as theta equals 3 pi over 4 plus pi as the answer. Right? Because to get to 7 pi over 4, I just add pi. And then to get to etc. So either one's fine. I understand break it down like this. It's just write it one way, but that's all I understand. Does that make sense? Okay. Let's see. I need to finish up doing the arc length real quick. So let me try to break her down real fast. Okay. So arc length. Let's make this really easy, right? We're going to use, right? Again, we might use X and Y as our kind of reference points here. So when I'm finding the arc length, I might try to find, I'm going to have an X distance and a Y distance, and I still want to add those portions up to get the arc length, right? But in this case, right, X is going to be some, R cosine theta, and Y equals R sine theta, right? But those are both functions of, R is a function of theta as well. So so I can kind of represent these as parametric equations. And if you remember when we were doing parametric equations, on the arc length, I would do dx over dt. In this case, I'll do x over d theta squared. And we're going to do plus dy over d theta squared. Okay, so taking up all these parts and adding together will give me the arc length of that curve. Right? Now, what's going to happen from here, right, is I'm going to substitute these with what we did at the end of the last section, right? Because we know what dy over d theta and dx over d theta both are. Right? They are, and maybe I'll write this out separately, right? So dx over d theta plus dy over d theta squared is equal to, now if you remember, dx over d theta is going to be dr over d theta cosine theta plus r negative minus r sine theta squared plus dr over d theta sine theta plus r cosine theta. Okay, so again, I just wrote down those expressions from doing the derivative, right? But if I square each of these, I'm going to get, and I'll maybe write it kind of so they're layered. I'm going to get dr over d theta squared cosine squared theta. Multiply these together times 2 minus 2r dr over d theta sine theta cosine theta. And then we're going to have plus r squared sine squared theta. And then we're going to have plus, now this is going to be this term, we're going to get dr over d theta squared sine squared theta plus 2r dr over d theta sine theta cosine theta plus r squared cosine squared theta. Okay. Anything interesting going to happen? Anything at all? What's going to happen to those middle terms? You have minus 2r dr over d theta sine theta cosine theta and plus 2r dr over d theta sine cosine theta. They're going to cancel, right? They're just opposite sides, right? You say, oh, that looks like the same mess, but they have a positive and negative sign, so those are going to cancel out. These both have a dr over d theta squared on it, so I can factor it out. And I have cosine squared plus sine squared. What's cosine squared plus sine squared? 1. These both have a r squared on it, so I get sine squared plus cosine squared. What's that? What's sine squared plus cosine squared? 1. So I get dr over d theta squared plus r squared. So this becomes the integral, and maybe I'll keep bounds on it. Of the square root of r squared plus dr over d theta squared d theta. That's my formula. Okay. So just nice. I just take the radius squared and then take the derivative squared. Okay. I'm just going to do 46 for us real fast. It's going to be pretty straightforward example here. So 46, we're going to have r equals 5 to the theta. So that was a little different, right? That's okay. We want to find the length of this. Okay. And it says to find the length of it from 0 to pi. So to do that, I'm going to take the integral from 0 to 2 pi of the square root of r squared, which is 5 theta squared, or 5 2 theta, plus dr over d theta, which is the derivative of 5 theta, plus 5 theta. I'll write it first. Right? The derivative of 5 to the x is 5 to the x times the natural log of 5. So we have 5 to the theta natural log of 5 here, squared, d theta. Now we're going to get the integral from 0 to 2 pi of the square root of 5 to the 2 theta plus 5 to the 2 theta times the natural log of 5 squared d theta. These both have a 5 to the 2 theta in common, so I pull it out. So we get, and then take the square root. So I'm going to get the integral from 0 to 2 pi of 5 to the theta times the square root of 1 plus the natural log of 5 squared d theta. Okay, what is this a variable? Is this a constant? Is this a function? What is this whole thing? It's just the number, right? So that doesn't even matter. So we're just taking the integral of this guy. What's the integral of 5 to the theta? So we have, so remember, whenever I'm taking the integral of a number to the variable, you write it down again. Well, then you divide it by the natural log of the number. Okay, you need to remember that. I gave that to you. That was chapter 6. Okay, and we have the square root of 1 plus the natural log of 5 squared. We're going to evaluate this from, that just came out, 0 to 2 pi. So we're going to get 5 to the 2 pi over natural log of 5 square root of 1 plus natural log of 5 squared minus 5 to the 0, which is just 1. Natural log of 5 square root. Okay, we can probably simplify this a little bit. I could probably rewrite it as 1 plus the natural log of 5 squared over the natural log of 5 times 5 to the 2 pi minus 1. It's the same thing, but okay. So I just plugged into the formula, and we were running out of time. So just choose that, right? Maybe I'll circle it a few times so you know use this formula. This should probably be the most straightforward of all the formulas, because again, it doesn't really matter what direction we do, right? Or okay, that's the arc length formula. You're going to use the find the arc length. I didn't get to cover the last example. That's okay. It was a bit harder one. I just thought it'd be fun if we had time, but we totally don't. So, any last questions for me? Anything? No. Okay. Awesome. I'm going to be backing up for a bit, so you can feel free to ask me a little bit if you want. I do have to run like right now, so I wish I could stick around longer, but I cannot, unfortunately. So thank you guys. Remember, there's going to be a test on Monday.